Okay, good evening. I wish to just take this moment and define on the application of divergence, specifically in fluid flows. That means we're talking about the flow of fluid through a surface area. Let's take for example the equation given by Q equals to IU plus JV plus KW up here, and the unsteadily velocity field of a compressible fluid. Let us consider the rate of mass flow out of an elementary cell, that's the x, dy, dz, which gives you dv, that's the sum of the volume, fixed with respect to the x, y, and z coordinate or axis, as you can see here. And now let's see, this is the fluid. Now it means that there's a fluid that is moving from this direction, that's from here, from this direction into the box. As you can see, this arrow pointing here. So the fluid moves from this direction and comes out through this other direction. Now our problem is to determine the velocity with which the fluid has inside this volume of space. That's from A, B, C, and D. Now, and also from H, E, F, and G. So we are to determine across this volume of space. Now, the mass that flows through the phase A, B, C, and D during the time interval, let's take the time to be dt, as you can see here, is rho, that's the density, times the volume that moves in, that's the initial volume that you can see here, U, through the area dy dx by the time dt, where rho now is the mass density. We need the mass density of this area. And then the mass that flows out of the phase of E, F, G, and H during the time interval dt again. And then now the general equation to express this is given by what we have below, rho plus partial derivative of pu dx in the dy dz dt direction. Similarly, the expression can be obtained for mass flow in the out of the other phase. The net mass that passes through the cell dv during dt is given by this formula. So you take the mass input plus the mass output times the z, the other component that was in the x,